Okay, so hey guys, I'm gonna use my monitor on the side here, so I'm gonna be looking that direction most of the time. But this will be easier, that way the screen is bigger so you can see what's going on. Okay, so we're gonna look at our CDR presentation. Okay, so for background, we just said when we were created, how we started as an organization, what our goal is, and that we're a part of this vertically integrated project consortium. And then after that, we get into system engineering. We give a flow chart of our team organization. We get into our mission statement. And then we describe our mission and system requirements. Okay, so we've seen some of this from previous presentations, so I'm not going to really get into a lot of these details. Okay, so we have system requirements here, and then after that we have our system design, how all the different components they come together. Okay, then after that we describe our mission or flight plan. So we have another outline here. So we focus on the competition. You need to have system engineering principles, develop this autonomous drone, and complete all the different tasks. So for scoring, there's three different components. There's a journal paper thing you got to write. Then you have to do an oral presentation for the flight readiness review. You have to actually go and do the competition and score points, the flight mission demonstration. Okay, and so as we said last time, we're going to just do two primary tasks, which are the autonomous flight, just the waypoints from A to B to C and so forth. And there's also search area, which is 4 million square feet, I think. And so all these secondary tasks we're not going to even look at or try to complete. Okay, so autonomous flight task, that was one we just go from waypoint to waypoint there. Then there's a search area task, large search area to find some targets, take pictures of, as we said before in the previous video. Then we talk about our flight checklist. So there's a pre-flight checklist, all the things we need to check before we actually go fly and do the mission. And then after that, we do the post-flight checklist. So after we land, what are things we need to do as we shut down and clean up? Okay, then we look at our mission operation, the time breakdown. So takeoff it will take about 5 minutes, and then it'll do 10 minutes for doing the waypoints, the autonomous flight. Could be 7 minutes or maybe 5 minutes, 9 seconds. We calculated that for the search area task. 5 minutes to land, and then 3 minutes of extra buffer time. So the total time is half an hour, 30 minutes. Okay, so the red line here is the no-fly zone, as we said before. The green area, this line here, this polygon, the search area is inside of that. And this blue line is the waypoints. Okay, so we talk about how we're going to do the search area pattern. We're going to do kind of this lawnmower pattern in these grid-like fashions. Like that, we give some key assumptions. Okay, then let's see. Do we have any comments here? We have one on the timeline. Okay, so let me go back. So on here we had a question. In your timeline, are we doing onboard image processing or humans identify the targets? Is this part of your timeline? So the answer is no, this is just part of this part here, the flying time. Where the humans identify the targets manually, that would be after this. That would be, oops, sorry about that. This would be in the post-processing time of 15 minutes. Okay, let me jump back down to here's after we talked about that. Then we looked at our flight path factors. So here we should have put a screenshot of our spreadsheet, how we calculate this instead of just putting all these different things. It's kind of hard to follow, in my opinion, as I look back at this. Okay, then we look at the horizontal field of view versus altitude. Okay, we did a vertical field of view versus altitude. We looked at turning radius. Okay, so here we have a question here. I don't remember the rationale or decision behind the type of search path. The grid pattern, did we consult with our mentors about this? So I don't think we did officially, but there's a function inside of this software called Mission Planner where it'll generate this lawnmower pattern for you for free automatically. And then we had another question here on this slide. Where does that equation come from? This one here. Can you explain its relevance? So you already know velocity and turn radius, so you really want bank angle. Velocity and turn radius are already known, which is what's plotted in the graph here. I think here we just want to be showing that if we're going to be flying at this speed, this is our expected turn radius. I think that was the whole point of the slide, but it's sort of unclear. And then We had another question. Don't know if this is for this subsystem. Why are so many people failing the task? Oh, that's this one. Hold on. Yeah, so why are so many people failing the task with commercial off-the-shelf autonomous items? We should focus our efforts on reasons why they failed. We're buying all these commercial off-shelf things. It's fundamentally that difficult to integrate these things together. So the answer was yeah, and this is also our first time doing this competition, so we didn't really have tons of experience. So that doesn't help at all. Did the students tell you they put the propeller on backwards? Oh yeah, so long story short, we um have one motor, and then we put the propeller on and actually put it on backwards. And so we're trying to fly this drone, and it doesn't go forward. It kind of turns a lot and it crashes quite often, and we can't get it to just fly straight. And so we went to one of our mentors, who's a Hawaiian Airlines pilot who flies RC planes for fun. He's been doing this, I think, like 20, 30 years. And so we talked to him, show him our problem. We show him the whole drone, the whole entire setup. He looks at it, he's like, okay. He says, well, I think your propeller's on the back. And we're like, what? He just takes it off and flips it around and puts it back on, screws it on, take off, and it flies straight and perfectly. And we're just baffled completely. Just wow, it was such a dumb, simple thing. And it solved the problem. And so this is what our professor here, as short for Dr. Shroma, was mentioning. Right. So and then the TA Brennan thought we bought the wrong propeller, but no, in actuality we just had it on backwards. So the kit had all the right hardware, the software we had was all correct, but we just didn't put it together. And that again goes back to like, hey, we have all this amazing equipment we bought off the shelf, but we just don't put it together properly. We're not a very experienced team. Okay, then let's see, we're gonna skip down. So the ground station software, we talk about how that works, and then how we communicate with the different components, and then to the judges eventually. We did a test with how that works. The target format of what we'd see at competition, some risk mitigation. I think we're still good. Yep, no comments on that. And we talk about image processing requirements. We talk about the workflow. This is a pretty good diagram. And then we look at some preliminary tests we did. We did look at some exposure, some of those settings. Okay, let me go back. So 42, all you've done to see that image is zoom in. So there's a target here within this red circle, and that would be this one, which we just zoomed in. Right. Okay, and then this is at 6400 ISO. I don't think so. I don't remember if we mentioned the ISO settings here or not, so I'm not too sure on that one. So our other comment we got is when you took that picture, were you running at 27 miles per hour? No, we weren't. We were standing perfectly still. So the reason why um, Dr. Strom was asking us 27 miles per hour is because the drone is going to be flying at 27 miles per hour. So it looks way too stable, right? That's what he's trying to get at here. Okay, so then after that, we look at some camera estimations, and then we looked at a camera comparison. And so the example here, example pictures taken with, yeah, so the example here in these slide 42, this camera, the Canon PowerShot GX9, he's asking if we took these pictures with this camera. And the answer is no. If I remember correctly, we had, I think it was this one, this Canon PowerShot S110 actually. I don't think we used this one. And then do we send a signal to turn off or retract? It's kind of risky if you retract or to have any signals because you could maybe lose communication. Yeah, I don't think we did that. I think it was just the manual trigger. I think that was it. But later on, we implement in the software, there's a way to do it where you just take pictures every 4 seconds. And then are we tracking any of the cameras? No, I don't think we did. Yeah. Okay, so that's the first page of notes we got. And then other ones we got here. So if you didn't circle this red, you wouldn't even know the target is there. So if you see an image where you're 300 feet away, can you even see the target? Or can you blow it up into eighths and then view each eighth? Yes, what's hard is we'd be flying at 300 feet altitude or whatever the altitude would be. But because the targets are so small, you're probably not going to manually see it. And we were going to do manual classification where we just show a person, here's the picture of the image, so they would see this one on the left. And then they would go look and see, is there a picture? I mean, is there a target in this picture? Yes or no? And then we'd have to classify it that way. We didn't have a autonomous way of doing it back then. The teams now have autonomous ways of doing it. So because of that, you might easily miss this. So there's a big concern that you might not have seen this target if you're doing it manually. So it'd be better if you can like break it up into eighths or section by section or something. And then if we also get some vibration, it'll blur the image, and then that'll be hard to find any targets. We had a question about how the camera's mounted. So there's a component underneath where there's like this, not like a bomb bay, but sort of similar concept, and then the camera just sits angled down, facing down. How many pictures were you taking? I don't think we took a lot. I think there's just one or two. And then how are you sure you want to take pictures? So this one, I think this for this test is just manual. But when we do this in real life, on board the drone, we have the camera take pictures every 4 seconds. And then you have how many minutes to go back if needed? So like less than 10 minutes. Like if you have 7, 10 minutes to view the targets. So if we allocated 7 to 10 minutes to do the search area, take all our pictures, land, come back, see if our people can see any targets in there. The question is, if you have some time, can you go back out and fly and get more pictures? The answer is technically yes, but I don't think we allocated a lot of free time to do that. If I go back to whatever slide that was, number we had a timeline somewhere. Yeah, I think it's yeah, this one, sorry. So slide 24. So if you finish searcher in 7 minutes and you have some extra free time, say 3 minutes or more, you can go back and go find some more targets. Like technically, yes. Okay, then no image processing, you're sending images. In this case, I forget if the plan at the time was to send images down in real time. But at the actual competition, what we would do is we would land, take the SD card out of the camera, put it into the computer, and then have our people just start manually looking for the targets that way. So we had a question on like what's onboard processing and why mention if it does not exist. Have we tested the camera taking pictures remotely? Yeah, so the onboard processing would be like there's a computer on the drone and it's connected to the camera. The camera take a picture saves onto the computer, then the computer sends that picture down to us. That's what we meant. We don't really describe it. Um, yeah, okay, so we transmit images to the ground station, and then we're going to use a Raspberry Pi 2 as the onboard computer for that. But I don't think we really go into that many details about how this actually works. It's kind of just high level. And so we end up just gonna do it manually at the time. Okay, then let's see. Would the other Canon camera be better? I think it's possible. I forget what we answered or how we answered that question. What's your projected capture rate? Yes, I think we didn't mention it here, but the actual competition, we took a picture every 4 seconds, if I remember correctly. And then when do you send the picture to the ground station? Yeah, so that one, I don't think we mentioned that either. But as you can see, there's a lot of questions about how all this process works, right? Because we didn't give a lot of details. This is very high level. Like trigger the camera, how does that happen? Where do you store the images? How do you send them down to the ground station? What's the connections for the Wi-Fi? What hardware do you need to make that? So those are all the important questions here. Let's see what else we got. Can we transfer many pictures in real time? The answer is no. We'd have to do this data file transfer protocol method. I forget how we plan to do it. I don't think we even mentioned it anywhere here. That's why. Because after that, we just get into electronics. Yeah. Yeah, but there's a lot of details here that you can see are clearly lacking. So for those of you who are working on your CDRs, you need to have tons and tons of details fleshed out. You don't want anything vague and general and high level like this. That's really a big no-no. Um, and so our professor is estimating that each person has only about 10 seconds to look through one image. Is that long enough? Again, it would have been nice to have some metrics about preliminary testing with our people on the ground to see if that's fast enough. We can also change the number of pictures if you change your altitude. So if you fly higher, you don't need as many pictures, right? You can cover more area. If you fly lower, you need to take more pictures, right? It kind of depends. There needs to sort of be that trade-off study, which also isn't here in these slides. Okay, we have more questions on image processing. So within overlap, can you still see the picture? Um, yeah, I don't think so. I'm not sure because we never tested that either. I don't remember how we answered that question. And then the TA said, Brandon said, you could maybe take a corner picture and then see what happens. We also said weight is more important than the lens parameter. I think, oh, what slide number is this? I didn't write it here. This must have been probably probably this one. The weight is more important than the lens parameter. Yeah, so we're probably looking at this one. So there's row, this is more important. The reason I think weight is so important is because the Penguin doesn't have large payload capacity. So it can't hold a lot of stuff. That's a big problem. So we're trying to look for something that's relatively lightweight. And it seems risky to retract the lens. Yeah, there might be delay, how you turn the camera off, how long does that take? Again, there's a lot of questions here and details that are completely missing. We could easily squeeze it in these 4 or 5 slides or just make some more slides to answer these questions and give more details. If your wireless band is huge, I would take more than 100 pictures. Yeah, I'm not sure how we answer that one. Um, we'd have to ask our guys who would do the data file transfer stuff from the drone down to the ground station. Okay, then we get to geotagging on slide 49. So if we're using an old program, what's the holdups and milestones? What testing can we do? So I think when we got to this slide, we said that we're sort of behind schedule on this geotagging test. And I don't think we finished finalizing the geotagging process until I think May. And at the time, this presentation is December. So I don't think 5 months, I think 5 months later, we finalized the geotagging process. But then we had the question, how do you tag every picture? Are they synced? Is it to the second? Yep, good question. I think we don't answer it here. We didn't know the answer. But turns out there's a program inside of Mission Planner, the ground control software. I believe, if I remember correctly, it's called like Geo Reference or something Geo anyway, or Geo something. But it's gonna help you do the time synchronization for your cameras and the taking pictures at different locations. Like you would know where your drone's GPS coordinate is and your camera's on your drone. And if you know that position, then it syncs up the images that way. So you can get a timestamp on your pictures. And then we had the question of the sample rate of mission planner and then 5 or 10 every second. We should have mentioned those details here in the slides, but I don't think we did. I think we answered it verbally. And I think it is I think it's 10 hertz, but I could be wrong. Got to double check on that. The ground station clock is synced with the plane. The answer is no. There's in that geo reference or geo whatever program, you have to give the time offset. So you have to punch it in as it does this process for you for free. And then you need to know what's the plus or minus GPS location on the plane because there's an error, right? If you're off by a second, an angle, then the whole thing is going to be off. Yep. So, and the main thing is you really need the GPS coordinate of your aircraft because your camera is attached to the aircraft, right? So that's the main thing to know. But of course, if there's going to be GPS error, then your camera is going to be off, right? So then you're going to get a whole bunch of problems in trying to figure out where's the target located in terms of where's the target's GPS coordinate. So those are all the huge big questions. And we got hurt pretty badly in image processing, I think, if I remember correctly. Okay, so we talk about some risks mitigation, and then we get into electronics. So this subsystem, we show a block diagram of how everything is set up. We look at the Pixhawk. This is the brain of the drone. And then we look at the battery curve here. I think we're looking at discharge or something. We look at the power budget, and then let me go back to slide 54. What's the x-axis? Yeah, good question. It's not labeled here. I think this is volts on the Y, and I think time is on the X. That'd be my guess, but I don't remember for sure. Okay, back to 55. Only the motor matters. Other parts coming in that we order, do any of those matter? We need some context of the missing parts. Yeah, so the motor is the most important. It draws the most current, right? And then I don't know if we've ever mentioned, yeah, we don't have like a total anywhere. So it's hard to say like the motor is like 90%, 95% of the entire power budget. And like the Pixhawk is 1% or 2%. It'd be nice to see that here. And then do the same thing for other electronic components that would be coming in. What percentage of the power is it consuming? Those type of things. Okay, this one, I don't know what it has to do. It's not that we don't, I forget what this comment's about. Um, see, backup power source. How does it know when to switch? Oh, it must be on this one here. Yeah, so somewhere I think when we were presenting this slide, one of my teammates mentioned the backup power source, but then I don't know if we mentioned like how does it explicitly know when to switch? Yeah, I'm not sure. And then we had another comment. Hopefully, we don't lose battery because I think we just had one big battery at the time. It'd be this one right here. Okay, then we have four radios. Two of them operate at the same frequency. And then we just had a comment. Generally, a radio transmits or receives. So if one is transmitting, the other receives. This might cause us to jam the signal. So that'll be a problem. And then how much gain of antenna, the bandwidth. How do you know if you're at full throttle? The minimum PWM signal to maintain throttle. If you're running full throttle the whole time. Yeah, these are a lot of specific questions that I think we don't answer at all here. This is just a high level block diagram of all the electronics and how they're all wired together. We should have put into more context about these type of details here. And then if we have a 10% buffer on payload, you're not going to be flying at 50% throttle because they were going to be too heavy. You have to fly faster. I think that one after risks, we probably mentioned that um yeah, so this comment here, I think 10% buffer payload, operational flight weight buffer 10.72%. Yeah, so you can't be flying at like half throttle if the plane is pretty heavy. And then we had another question like, where's the wires in the payload? Yeah, it's not there, but it does add up pretty quickly because there's a lot of wires. And there's batteries aren't included here because yeah, I'm not sure that should be here too. I'm not sure why it's not there. And then are we flying at this weight? No, I don't think we're flying at this weight. This does include the actual hardware. Oh no, this one. I think we were flying it this way, 4.73 pounds. This is about different weight of all the components, but we should have included batteries on that one. Oh wait, this one. What percent of that weight is missing? There's additional 40% more to add on. I'm not sure where that 40% is coming from. Maybe I wrote this wrong when I was writing my notes. Maybe I meant 10%. Still need if we can fly, touch, and go at higher weights. Yeah, so we had a comment about like if you weigh the penguin down this drone a little bit higher beyond the typical payload capacity, try to take off and see if you can. And if you cannot, then just try to land and then maybe take off weight, try to do the same thing again. And then see if the manufacturer just being conservative on your maximum payload capacity or not. And then therefore you actually might not have a 10.72 buffer. It could be more. We don't know. And does this 10% take bigger motors into consideration? Yeah, it should. Yep. Okay, let's see the next wave of questions. This flight wave is with the bigger motor. This one, yeah, I forget. I don't remember. Not sure on that one. I want to fly with the factor safety of 1.1. Okay, so we have some FEA's analysis somewhere, I think. Okay, here. Yeah, so fly with the factor safety of 1.1. Probably not. That's way too close. Or maybe this is type of 1.01. Like this rod is most likely going to break. We could add some dummy weight to find the CG. That's on this slide here. And then we have a unit issue here, pounds and ounces. So we should choose a unit system and just keep it consistent throughout the entire presentation. So here we have inches, we also have pounds, but I think here we have pound mass, miles per hour. Here we have pounds again. Here, okay. But anyways, so pick a unit system just to be consistent. Probably somewhere earlier we mentioned like meters or something. Okay, then let's see what else. On 62, according to this, you need 1.75 pound mass and 50% throttle. Is this for static thrust test? Dynamic thrust reduces exponential speed, because be as much as 60%. So we said cruise speeds at 50% throttle, and then here are all the different variables and components in our equations. But when I look back at the slide now, the slide's kind of useless. Like, what's the big key takeaway, and what is the value of the required motor force? It's not anywhere on this slide or on the next one, really. We don't have any curves in that either. Yeah, so this is pretty lacking in detail and explanation. But if you have 1.75 pound mass, I think you meant 8 or actually, well, I don't know where that 1.75 is coming from. Oh, let's see, throw all these numbers in. Okay, maybe you get 1.75. I don't know. But no, I don't think this was a static thrust test. I think we got some real life data, real world data from the telemetry data. We might have tried to calculate it that way. But either way, this slide and this slide, it definitely needs some rework. It's not very helpful. It's hard to understand what's the main key takeaways and how we're getting into these numbers or where our professor got 1.75. And then we should be able to go back and verify the equations that we've showed here. If we have all this telemetry data, and that's important. It can put accelerometer inside the plane or inside um with the phone. Yeah, we could do that. Although the drone does have accelerometers in that Pixar, so we can use that information when we land and take out I mean not take out, but extract the telemetry data from a previous flight. Is that how you balanced it for that flight? I think I gotta really work on my note taking at the time. I didn't put the slide numbers for a lot of these things. I think it's this one. We said the datum is the nose of the aircraft at the very front. We wanted a CG location 16.09 inches um, from the nose, and the total weight cannot be okay. So that how you balance it for that flight? I believe this is how we did balance it for the flight. This one that we were mentioning here. Yeah. Okay, then 466. Assume your material properties are correct, but there's something scary here. At a factor of safety of 2, so here on the right, your plane is going to be destroyed at a 60-degree bank angle. So right now, this is the plane is just flying straight. So when you're flying at 60% bank angle, the forces on the plane's wing is going to be a lot higher. So 1G is never enough for a wing. So when I'm turning or climbing, it's more than 1G. So Boeing applies a dynamic factor and then a factor of safety. But if we don't know our material properties are correct, then it's kind of useless. So in any FEA CFD, we need to know the material properties, the boundary conditions, and then the forces, the load conditions. But because this material is some sort of foam, and then I don't know if SOLIDWORKS has exact material properties, this whole analysis is a little bit uncertain if it's correct or not. And so because you don't know the correct properties, our professor said it's just saying that this is art, that this thing is going to break and these values are garbage. And yeah, it's a little harsh of saying it, but yeah, it's true. Yes, then TA said the same thing. This art saying the plane's going to break because if the factor safety is 1, or if this is at factor safety 2, but you're flying straight and then you bank, then you're going to get a lower factor safety. And then this is not going to survive any turns or just generally, this rod's going to probably break pretty quickly. Yeah, so the aluminum rod fails. The factor safety is close to 1. So something's super wrong here. The wings are going to break at takeoff, but in real life, it doesn't break. So this whole analysis is incorrect. Yeah. Um, so the flight conditions aren't the same thing as loading conditions. The loading condition of the forces. So our professor suggested make a table and then list all your forces. And then look at your analysis again. And then if it breaks, then okay, but there's errors somewhere here. Okay, then we did some risk mitigation for the aircraft, and we ended with project management. So, so this Gantt chart here, we had a question. Make it simple for me. Are we on track, far behind, or somewhere in between? So the yellow stars, they represent, I think, things that are behind schedule. So this one we're behind on. The red line represents today, but then this yellow star is in the future. So we're like ahead of schedule. Um, oh no, we're behind schedule a little bit on that one. That's like the next big thing that's upcoming. So I guess when we presented this, it was kind of confusing. So we should have just said we're behind schedule, on track, or not. But then according to our Gantt chart, we're on time. So the red line shows that we're on schedule. So all of these shaded areas um, intersect the red lines, which means you're actually on time. Then we're asked the question, when's your proof of flight video due? So this is for the competition. You have to demonstrate that your drone can fly and do that by recording a video. And so for March 14th, we have like 2 months. I think that would be in the spring semester. Yeah, okay. Then we had a question, are you gonna work during winter break? I think we said no. The last date we have here is December 18, 19-ish. Yeah, so we didn't work during, yeah, the schedule doesn't include a winter break. Um, but the trade-off though is a lot of work can get done in break because there's no classes, no more final exams, no other projects or things to worry about. So just something that we could have thought about if we wanted to work during winter break. because right now we don't have anything here. But then we had a question about is 2 months enough buffer time? So normally I would say yes. How much average buffer time have you eaten? So this, for everyone who's writing Gantt charts, making Gantt charts, this is another important thing I want to pause on. Your Gantt chart should always be answering three questions. Number one is, are you on schedule? Which is the first question we got. Other one is, how much of your buffer time have you consumed or eaten? And then the third one is, if you're behind schedule, what's your plan to catch up? So those are three questions. Maybe I'll make a Gantt chart video later on. Okay, so in theory, you could make the proof light video on March 15th, and that'd be like the earliest. Yeah. Um, let's see. Then we had some other general comments here. You should clearly state your subsystem deliverables. If goals aren't set, how can you finish in 3 months? And then when this guy, Jay, I think this is Jonathan, he was a grad student at the time. When he was on this project, they had some buffer time, but we didn't finish. So it's important to have something written down, what to expect and when it should be done. And that way you can see how much buffer time you've consumed or not. Uh, our professor was saying, I remember a time people wanted to buy a kit for practice, then make her own. Yes, I mentioned that. The long story short for this one, there was a team, I think the year before us, who wanted to buy this drone kit, it's quadcopter, get it flying, and we couldn't get it flying. But some people still wanted to make their own drone. So the professor's like, if you can't get the kit drone to work, why are you gonna work on making your own? Then let's see, we had another question. How are we documenting outside help with our mentors? It's mostly just emails, but we should have organized that somewhere else. And then how do we document progress? We can't hide daily progress. So we're running Scrum, doing daily stand-ups. And then we had spreadsheets about they're doing this today, they're planning to do this tomorrow. Do they have any obstacles? How are we going to address that? Um, then Artia Brennan asked John, you don't think you're allotting enough time? Yeah, I think you're worried about the schedule. It seemed too aggressive. So he thought we're underestimating how much work we have left to go. And then our advisor said, for 19 years, he's never seen a project finish. And he's like, maybe it's me because I'm the common denominator. As sort of joking. Let's see. So John's like, he likes Scrum, but what do you do when you're behind schedule? So this is where we have to be kind of proactive and look at, okay, we have this obstacle, this is the task. Do we add more people? Do we change people? Those kind of things. We have to strategize. Let's see. Do we have an understanding when things fall off on the schedule? If we get to the end of the week and things aren't done, and then things start stacking up and compounding, we trade money or performance to make up for it. What are those trades and when do we make those trades? Yes, this goes back to like our Scrum, talking with our teammates, seeing how they're doing, those kind of things. Why do we think pilot safety is a three in likelihood? Um, I forget. Yeah, it's a good question. I don't remember why we said that here. Oh wait, pilot safety is a three. Yeah, I don't know. We should have explained that better. Is there a 50-50 chance the plane actually hits someone? No, it shouldn't be. But the way that it's shown in the risk cube, it is 50-50 chance. Other general comments we got is just to remind us Boeing money is only for technical costs, so we can't use it for travel to go to the competition. Projected budget, we had one down here. Travel expenses, it's listed here at a high level, but this includes plane tickets and hotel, I think. And then this is for 10 people. I believe it is for 10 people. and the cost is probably more expensive later. We should decide who's going, and then we can save money. And just put people written down, even if they're on the fence. And we had a question, how much does it cost to go to the East Coast? I think it was like $1,000. And then our other professor said, have you heard of kayak? It tells you when to buy and when not to for plane tickets. Another question we had, the size of this field is comparable with the search area. This field here, Kauai Nui for where we were doing our flight testing on the east side of Oahu. And then why don't you have safety glass if you're throwing it, especially with rotating parts? Is your safety pot stay stable? So we went to the field, right? And the guy he flipped or put on correctly. He did say it flies stable, right? But we didn't have safety glasses. I think he just had maybe sunglasses. Um, yeah. Then what do you do if you lose connection with the drone? There's a built-in feature. You either continue on the mission or you fly back home. There's a significant development risk, not just project management. Yeah, so there's a lot of those image processing risks, electronic risks, the question about the factor of safety, if this is correct or not. And so there's a lot of potential big problems, like things could go wrong. Okay, and I think, yep, that's the last set of notes. Um, so overall, we got pretty beat up at this CDR presentation. I remember it very vividly. But the main thing is to stand your ground, answer the question best you can, don't make up answers, and then do address the comments, feedback, and then I think we did a lot of that when we got to our CDR report. But the presentation came before, and that's why I think we had a lot more questions here than we did at the report. But overall, I think we did decent. We have, I think I have the grade. Let me pull up the grade. Oh, sorry, I lied. We didn't do that great. We got 60% out of 100. So for introduction, we got 7 out of 10. The strategy and big picture, 7 out of 10. Technical details, 5 out of 10. Yeah, you can see that, right? We can tell we missed a lot of details. Effectiveness, communication, delivery mechanics, 7 out of 10. Conclusion, 7 out of 10. The time was 3. I think we went overtime. So that's why we did so poorly on this one. 3 out of 10. The visual aid, 7 out of 10. So at best, we seem like we're average on a lot of these things. So we didn't do outstanding in any one category. Yeah, so those are all the things that we did wrong at CDR presentation. So I hope you guys learn from our mistakes and see you guys next time.